Welcome to our new course in the area of probability and statistics. This class is intended to give us some introduction into some of the topics that you might have seen in a discrete mathematics class involving sets and combinatorics and things like that. So we'll start the course by focusing on what is probability and the different types of using data to calculate probability, and then eventually migrate from that into statistics and probability distributions and predictive modeling. And then toward the end, if we have some time left, we might actually get into some numerical methods type of topics that aren't necessarily probability and statistics, but would be found in an undergraduate engineering mathematics class. All right. So this class is centered around a textbook by J. DeVore called Probability and Statistics for the Engineering Sciences, for Engineering and the Sciences, the 9th edition of this book. There isn't a lot of change from one edition to the next that I've noticed, at least for the topics that I choose to cover. But just so that we're all up to date, this will be kind of our reference for that one. So if you've got a copy of that, that's great. I like the flow of the book because he breaks it down in a very logical approach. And so if you look, we're going to break this into kind of the different types of statistics. So the first chapter in his book, he starts out kind of describing data and how you analyze data and how you can, just by looking at the numbers, can come up with certain trends and patterns and stuff. Okay, and these are what we call descriptive statistics. And so that will be your chapter 1. Basically, you can see some of the features where the highs and the lows and the peaks are and those kind of things. Once he gets into a little bit later in the book, more like chapter 6 through 16, we're going to get into more of the inferential statistics, okay, which basically involves drawing a conclusion about a population based on sample data. All right, so it's kind of becoming forecasting and predictive modeling, and those kind of things will fall into this category. Then in chapter 2 and chapter 5, before we can get into these inferential methods later on, we actually get into the basics of probability. And this is a very important topic and very useful. And I do things a little bit differently. I try to be a little bit more graphic in my approach to it, just because for me, it helps me visualize what a problem is doing and what a problem is asking a whole lot better than otherwise. One of the biggest problems with a probability statistics class is always that just the nature of the questions that are asked on homework and in exams. It's a lot of word problems and a lot of data, and sometimes understanding what they're asking or being able to correlate that back to an equation, it can be a bit of a challenge. So I want to kind of warn you going forward in this series that it's all about interpreting the wording of the problem. Okay, don't try to memorize formulas blindly in a probability and statistics class. That's a surefire way to get a C or a D in the class. If you just try to apply a formula that's written down for you, you've got to understand how that formula came about, because every problem's a little bit different, and a lot of times those stock equations that are provided for you may or may not be completely applicable to any given situation. Okay, so I'm going to try to kind of walk you through what they do, why they do it, and then how to generate these equations yourselves. So that's my intent on this. All right, so we're getting into some topics with descriptive statistics, and so we'll kind of go section by section through the book and kind of highlight some of the bigger concepts that come out of it in most of these sections, and then we'll kind of stray off on our own and do some things on our own. Okay, so the textbook starts off kind of outlining what the book does, and then it jumps into doing pictorial and tabular methods for these. All right, so variables that you might have involve the number of observations of variable x. Okay, so you might say I have 32 outcomes or 32 observations or whatever the number is. Okay, and so we'll see a lot of n equals stuff, and we'll find out when we get to actual inferential statistics that the n plays a huge role in our accuracy and our confidence in whatever our prediction is going to be. All right, whenever you see something that says like x1, x2, all the way up to xn, these are the individual data points associated with our variable x, and we'll explain a lot more here. Probably around lesson 5 or 6. We'll start getting into random variables, because those become key to being able to establish probability distributions. And then from there, I can start doing some pretty amazing and powerful things with that. All right. So where it all starts out at is what do we do with a pile of data? You've probably been in a lab at some point, a chemistry lab or an engineering lab, and taken measurements and readings, and you have this big pile of numbers, or you've gone out and done an experiment or a survey or something. Trying to make heads or tails of just a batch of numbers can be pretty hard to come up with. All right, so the first method we're going to show you is what we call a stem and leaf display. Okay, and so the basic steps for doing this, and I have an example that we'll work through, is that the first step is we're going to select one or more leading digits out of the data set. Okay, usually it's the first digit, but it doesn't necessarily have to be. Okay, those become the stems. And then the trailing digits, everything else other than what you chose as your highlighter, become the leaves. Now, it's not quite as simple as that. You have to kind of look at the numbers and figure out, how can I break this up? For example, maybe I have a batch of data that has just three numbers, 83, 87, and 82, right? If I choose my stem as the 8, what happens is this 8 that's here is common to all three of these. And so all of this data would wind up in that same category. Okay, and so you wouldn't be able to see a whole lot. You just know, I got one category, it's got 3 entries in it. But if I start breaking this thing up, and maybe I make a category that goes from 80 to 83, and then another one from 84 to 87, and all of a sudden these start to get compartmentalized a little bit better, and you start seeing some things. And like I say, we'll show you some examples of what we can do. All right. So what happens is that once we've done that, okay, we're going to list the possible stem values in a vertical column. Okay, now again, vertical, just for the sake of conserving space in my paper, you don't have to do it that way. You're just going to create categories associated with the stems. Okay, and then you're going to record the leaf for every observation beside its corresponding stem value. So, and I'll show you here in a sec. Okay, and then we're going to indicate the units for the stem and leaves, on our display. All right, so one of the examples that we look at, okay, which is actually 1.7 out of the book, is trying to figure out, well, how many stems is enough to quantify a set of data. All right, so what we have is kind of an example of data that we've created a stem and leaf plot. If we look, the way this is read, this 3L, 3H, this is 30 low. We split the 30 category. So we have a data set. I'll just write the first couple for you. That is 31, 35, 36, 36, 37, 38, and so forth and so on. So you can see 31, 35, 36, 36, 37, 38. The next one becomes 40, 40, 40, 41, 41, so forth and so on. Okay, and so that's kind of the way the data is. Normally you will take the data, you will sort it. It helps make this process a whole lot easier, but you don't necessarily have to do that. You can kind of move back and forth and add things. I like to rank them in order so I can kind of see, how many of the 40s did I have? How many of the 41s did I have? And those kind of things. But the question becomes, well, how many of these stems is typically enough? Okay, and so the rule of thumb is that you take the number of data points that we have on here, and I take the square root of that. And generally that will give you a good distribution of the way that the data sorts out. Okay, because if I look, I have somewhere between 5 and 20 is generally a nice number. You don't want to have one group because then all the data is in that one, and you don't want to have 1,000 groups because then it's so spread out you can't see any of the trends or the groupings on those kind of things. All right, so for this particular example, what we did is we set our stems to be our tens column, and we set our leaves to be the unit numbers associated with that. Okay, now as we said, I think it was 42 data points tied out in this. And actually, maybe less than that. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Okay, 36 data points. I miscounted. All right, so I've got 36 data points on this. And so if we look, our lowest value was 31, and our highest value was a 75, okay, which came out of this last category. So if I looked at it, I had 36 of these. The square root of 36 ends up being 6 categories is what they're recommending. Well, the problem is that I go from 30 to 70. How do I break that up into 6 categories? Okay, so again, this is a rule of thumb. You don't necessarily have to do it. So what I chose to do is I went a few more than that. Okay, I could have done, the 30s, the 40s, the 50s, the 60s, and the 70s. That would have only been 5, and that's just not quite enough. So what I did instead is I broke these 30s into a low and a high. Okay, and so the way that works out is that it's a 30 low And so my low I defined as being 30, 31, 32, 33, and 34. And my high being 35, 36, 37, 38, and 39. And so I did a low and high category on every one of these stems. Okay, and when I took my data and I sorted it out into this, I started to just kind of throw these data pieces over into here. And so I had in my 31, 35, 36, like we talked about, and the rest of them. And I started to get this pattern of data to show up. And once I do that, all of a sudden, I take a pile of a whole bunch of numbers, and now I can start to see some things. I mean, the first thing that looks out at you is that I have more numbers up in the 30s and 40s than I do in the 60s and the 70s. So this is what we call the skewed distribution, meaning most of the data is tending toward one side. Okay, I see that I have the most values showing up between 40 and 44. Okay, that's indicated by this peak that's the longest of the peaks. Okay, but I do see that, and it kind of increases. There's a hump here, and then it comes back down, but then it starts to go back up again. So there's a secondary hump that's occurring down at that 6 highs, which is 65 through 69. So all of a sudden, just by playing with these stem and leaf plots and ranking things, just something as simple as what we've done here, you can start to see a whole lot of information and a whole lot of patterns developing on the data. So I also noticed that there's nothing between 70 and 74. So my question becomes, all right, is that the true nothing there, or is this one that's by himself out a little higher than everything? Is that an outlier, an error in a reading? All of this stuff starts to pose a lot of questions that I can do coming out of my basic stem and leaf plot. Okay, now, like I say, a couple of comments about this methodology. The data does not have to be sorted. Got a little bit of a glare on the light here. I'm going to see if I can fix that for y'all. A little bit better. Okay, and what this will do is that this will show our extreme values, or typical value, number of peaks, and our peak locations. Is all the data that you can come out of this, and so that's pretty handy. Okay, now you can go one step further and say, well, in this 4L category, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 12. 12 items in that category, and I had 36 total. Well, that's 1/3 or 33% of the data showed up in that category. And so all of a sudden, even just doing something as simple as that, I can start to work my way into calculating percentages, and a percentage is a probability on this. Now, there are some other assumptions that have to take place, but that's kind of the basics of what we can do with our basic stem and leaf plot. Okay, all right. Now, the next iteration of this that we'll get into then is what we call a histogram. Okay, now a histogram is similar but a little bit different, and what we do and we modify this is we start using discrete data. Okay, which is what we had before. We had distinct values for diameters of trees, or number of hairs on on your floor, or whatever. I don't know, whatever your discrete data wants to be. Okay, but the histogram, instead of calculating the actual data that we have, they start calculating something called a frequency. Okay, which is basically the number of times a specific value occurs. All right, so if we look at this, so the frequency associated with our last example. Let's see if I can get that back here. Our last data example is that the number 40 showed up 3 times. So the number of occurrences of 40 was 3 times in our data set. Okay, and so you can start plotting, just basically the number of occurrences. Now, one of the drawbacks of a histogram is that we start to lose some of the data when I start to make these plots. Okay, so we can deal with frequency. We can also turn around and calculate what they call the relative frequency. Okay, which is basically the frequency divided by the total number of data points. Okay, and now again, that's getting into a percentage. So the number of times that 40 would have showed up in my last example was I had 3 40s over 36. This is a 1 in 12. Okay, and then I can multiply that by 100, and that becomes our percentage of the time that the number 40 showed up in the data. Okay, now a histogram, what that is it's a plot of frequency or relative frequency versus value. Okay, all right. Now, one of the things that's kind of cool about the difference between these, well, frequency, if you add up all the number of occurrences you get back in, if I add up relative frequency values, because I've divided by n, everything will add up to 1.0. Okay, well, that's a fancy way of saying 100%. That if I've accounted for all the data, it will always sum. So relative frequencies can actually kind of check themselves. Okay, and then we can start asking simple things like proportion questions. All right, okay, all right. So that's kind of where we're going with our histograms. Now, we can, like we showed with the stem and leaf plot, we've got some general shapes, and so some terminology would probably be in order for us here. Okay, so we've got our, what we call a symmetric unimodal, meaning that there's a peak and it's basically the same number of points to the left as it is to the right, okay, and that there is only one peak. So that's a symmetric unimodal histogram shape. Okay, the bimodal was the one that we saw in our stem and leaf plot that had two basic peaks, okay? It had two peaks. Now I don't care where they are. I don't care that one is higher than the other. It's just it has two distinct peaks. We talked about skew. So if it's skewed to the left, it's a positive skew. If it's skewed to the right, it's a negative skew. Right? And so those are all very good for kind of describing the data or the shape of what the data is doing. Now, it doesn't give us any specific facts about the data. It just kind of tells us, oh, it's, most of the values are smaller, or most of the values are larger, or they're all centered around this number. Okay, but we need something, some more calculation type of methods in order to be able to fully and accurately describe data in a much more meaningful way. Okay, so that leads us into our next section, which would be things like the measures of location. Okay, all right. So what a measure of location does is it provides specific information about a group of data. Okay, and so most of these you've heard before at some point in your past, all right? And the most popular one or most common one is the mean or the average of this, okay? And so this textbook is going to write the mean as being an X with a bar over the top of it, okay? And basically, as you know, to calculate the average for an equal likely outcomes situation where everything has the same probability of occurring, I take the sum of the numbers and I divide by the number of numbers. Okay, so if I have 1, 2, 3, 4, and 5 on this, then I'm going to do 1 plus 2 plus 3 plus 4 plus 5 divided by 5. So that's 6, 10, 15 divided by 5. My average is 3.0. That's all you're doing. And we've done this, 1,000 times through our careers in high school and into college and those kind of things. All right, so that's a sample mean. It's based off of a sample set of data. Okay, now here's the thing that's kind of interesting is that when we start talking about measures of location and measures of variability, we also have to consider, are we looking at a sample, which is a subset, or are we looking at all of the possible data that exists for that particular problem, meaning the population? Okay, and so we write these things a little bit differently. Sample mean gets written as X bar. Population mean gets written as the Greek letter mu. So it's that micro prefix. So that will be a difference. And here's the reason that it's important to be able to distinguish between the two. Suppose I want to know, I want to do a poll of everybody in the United States and who they think is going to win the next presidential election on those. Well, there is no way that I could go and ask every single person what their opinion was, right? So the population is the population of the United States. But what we do instead is maybe I go out and do a survey, at my local mall or stand on a street corner and I survey the next 100 people or the next 1,000 people that come by to try to get their opinions. That's the sample. And what statistics does is it attempts to take the sample data and use it to predict out a population value, and a population value that may or may not be possible to actually measure. So we want to come up with predictive ways to do that, and then to know, well, how accurate was your data, or how accurate do you think you are? Okay, and kind of come up with ranges of acceptable values. Okay, all right. The other thing about a sample mean is that it is very sensitive to outliers, meaning that I had my numbers 1, 2, 3, and 4 as my data set. Okay, that's pretty good. But if I add one data point that is 3, 4, and 100 on this thing, then my mean of this set is going to be way different than the one that was here. So if this is an outlier, meaning it was a bogus reading or an error in how I gathered the data or something, this would be considered an outlier. And we'll show you some tests on how you conclude that as well as we start to move forward. Okay, so that's our first measure of location, is the mean. And we'll do a lot more with this. I'm just trying to get some ideas. And you guys have all seen this before, I'm pretty sure. So that's not an issue. Okay, the next measure of location has to do with the sample median. Okay, and so what the median is that's the middlemost point of a set of data. Okay, to get this, I must sort the observations from smallest to largest. Okay, and then basically you find the middlemost value in that data set. So if we have a data set that is x1, x2, all the way out to xn are sorted, then I'm just going to look for the middlemost values. So For my last problem here, the median of this was 1, 2, 3, 4, 5 values. The middlemost point is the guy in the middle, so it's that third value would be my 3. Okay, so if I have an odd number, it's a pretty easy process. But if I have an even number, like what I had up here, the question becomes, well, where's the middle? Okay, number 2 isn't the middle, and number 3 isn't the middle. It's actually like the guy 2.5. So what we do is we take the 2 on either side and we average them together. And that's the basis of how you calculate a median. Okay, so your book will write this, that the sample median is x with this little squiggle over the top of him. Okay, and so x is equal to the data point x sub m, where m, the index of the number, is equal to n plus 1 divided by 2. That will get you the average if n is odd. All right, and so that's how we were able to find that value. So in my case, it was 5 plus 1 divided by 2 is 3. So I took the x3 data point. This was 1, 2, 3. That's how I got it. Okay. If n is even, then we said that m is going to be equal to n divided by 2. So for the uppercase, I had n divided by 2. So is going to be, I had 4 data points divided by 2 gets me a 2. So then this guy becomes x2 plus 1 or x3 divided by 2. Okay, and so that's how we come up with those values, and that's how I know my average on that would have been 2.5 for this one, and it would have been 3 for this one. Okay, so what we notice in doing all this, there is also a population median, although it doesn't get used a whole lot, because again, if you have an immeasurable population, this one's kind of hard to predict, or how do you know that it is the middlemost point? Okay, but the power of the median is that it is less sensitive to outliers. So if I have data that is jumping around all over the place, okay, I can use a median to give me a better idea of what the middlemost value is, rather than worrying about the average. Although most times in practice, a lot of people will report the average, and then when it jumps a lot, they kind of go into a panic in data science terms. So that's what we're showing. So for the data set that I showed you earlier, here's what we did. Now for this, because I only have 4 values, and this is my population, because I have no other values other than this, we're using mu. And so the average of this we showed you was 1 plus 2 plus 3 plus 4 divided by 4 gives me an average of 2.5. Okay, and the median value using our median formula said that the mu was 2.5. Right. Now, for the last case where I added that 100, that outlier out on the end of this thing, the average moved all the way up to 22 when I do that calculation. But the median value in this list of data only moved to 3. So you can see that there wasn't much movement in the median, even though I threw this one crazy number. I mean, I could have put 1,000,000 on this thing, and this wouldn't have changed. It would have stayed the same, because this is a rank order of the data. Okay, whereas the mean for the average of these values moved significantly based on that one extra value showing up. Okay, and so we can start to kind of figure out some things, based off of, impact of values and that sort of thing. All right. Okay, and like I say, we'll define an outlier a little bit further numerically later, and then we'll start providing some tests to prove how something is an outlier. Okay, all right. All right, let's see. All right, so with those two armed for us, that works out pretty well for us. We're going to look at now, in this case, what we call, man, the glare's back again. That's a good way to drop the camera. That's your entertainment for today, right? Okay, all right, let's try this again. So we've got our measures of variability is our next category, because while on histograms in our data set we were calculating x bar or mu as a single value, I can have multiple data sets that have the same mu or x bar value associated with them, but what will happen is that those data sets may have completely different shapes. Maybe sample 1 is a whole lot of data that's centered right around that value that got me that average. So I would get a higher peak in this histogram around that value. But I could also have a data set that's much wider, that's centered at that same point, that's spread out a whole lot more. So we need a measure of kind of how much this is spread out, okay? And that's what we call variability, okay? And we'll calculate those with some calculations I'll show you here. So like I say, the average usually is not enough to describe data by itself, because I know where it's centered at, or I know where the average value is, but I don't know the overall shape of the data as we start to look at that. All right, so that's what we're doing here. see. Okay, so here's what we're going to do. Okay, so we're going to assume a data set that goes x1, x2, all the way up to xn. Okay, we're going to define then something called the sample variance. And they define that as s squared, and it's the sum of this equation. So it's the sum of, from I equals 1 to n of each of my data points minus that average value. Okay, so I take the difference between each data point and the average value. So basically that's a measure of, if my data was doing this, and I'm looking at this data point, say that's x3 and this was x bar, we're looking at that difference. Okay, it's kind of a measure of how far away it is. And then we're doing we're summing up kind of a distance squared kind of calculation associated with that. So that becomes my s squared, and then I'm going to divide it by n minus 1. And this comes out of some predictive modeling and some statistics that we'll show you, here in a couple of sections further down the book, like chapter 7 or chapter 8 was where that will start to show up. All right, so what they do is you can also, I've seen it written also where they take this summation term up on the top, this xi minus x bar squared for all of the data points, and call that as some sxx value, and then divide that by n minus 1. And again, n is the number of points that came off of this. All right, so sample variance is, kind of that measure, it's the total of the measure. Now, in practice, a lot of times we don't use the variance. Instead, we prefer the standard deviation. And so we have the sample standard deviation is simply s, and that's the square root of s squared. Okay, so we calculate the variance and then take the square root, gets me the standard deviation, and then this becomes what usually gets reported. You take a test and say the average was a 76, but the standard deviation was 9 points. Tells you a little bit about how the data was spread out and kind of the expected range of values accordingly. Okay, now there is also a population variance and a standard deviation. Okay, so our population variance is sigma squared, and our standard deviation for the population is sigma. Okay, but what changes is the formula is a little bit different, because if I include all of the data points of the population, I don't have to make a correction for the unknown. And what will happen is my sigma squared becomes xi minus mu, quantity squared, divided by n, where n is the population size. And so there's a little bit of a difference here. So for very large data sets, it doesn't make a big difference. But if I have a sample that has, 5 data points versus a population that has 100 million, there can be a drastic difference in these predictions for the sample variance and the population variance. Okay, now you got to kind of ask yourself, well, which one of these is easier to compute? Okay, and if we come back and look at it, it's all I have to do to compute my s squared term up here is I just need a sample of data. I don't have to have all of the points in the population. Again, it goes back to that that survey example that we gave a little while ago, that with 300 million people in the country, or however many they are, I know it's more than that now, but that it's impossible to get all of these data points, that there's no way for me to possibly know what this mu value is. So the sample becomes a much easier thing to calculate, but we have to make some corrections in order to make this prediction model start to look better than this prediction model. Okay, so s squared requires sample data, okay, and sigma squared requires population data, and often we don't know this value, or it's an immeasurable quantity. All right, so that's one of the things. Now, so to compensate for the difference between these two, this x bar and this mu, that n minus 1 factor that we saw is used in sample calcs rather than the n. Okay, and that will kind of get us going. Now I'll show you one other formula for calculating the sample standard deviation. Promise we'll get this lighting thing figured out here in a second. There we go, try that. I think that's better. All right, so we've got s squared, it's the sum. This was our formula for the sample standard deviation. Well, if I expand this thing out, we can actually say that this is the sum of the xi squared minus the sum of the xi over n quantity squared. I can write this based off of those calculations. It's kind of an alternate formula for being able to do this exact calculation. Again, n minus 1 is still in the bottom. And we'll show you some other shortcuts for calculating this. Calculating the variance and the standard deviation is a big process, especially for large data sets, because you have to include every data point has to be included in that particular calculation. So anyway, that kind of ends our first lecture. I know it's a little quick and a little fast. So a lot of the terms that you've seen in there, we've seen before. Okay, but we're looking for the mean, we're looking for the median, and we're looking for the variance. Okay, or the standard deviation will get you those. Okay, and again, you've seen all of these before. That's why we kind of went through it fairly quickly. So anyway, I hope that will get us going. We will have some more topics coming at you right away, and we'll get into something a little bit more interesting and more exciting. But I have felt like we needed to set up the textbook. We needed to set up just kind of some of the basics terms and kind of how we can display data. Remember that data as a pile of numbers has no meaning. It's not until you try to make a plot of some sort, whether it's an XY plot or you make a stem and leaf plot or you do a histogram, does it start to actually make some sense. And once you make that plot, now all of a sudden you've got a graphic that can actually help you visualize what's going on. So we're looking at things like, modality, how many peaks did it have? We're looking for things like skew. Was it more to the left, more to the right? And so forth and so on. So these are all kind of concepts that you've seen before, and we're going to file these away in the back of our mind as we start to move forward from here. All right, so hang in there, and we will move on to the basics of probability in our next lesson. Have a great evening. Happy engineering.